In this video, we are going to discuss about sine wave generators. So, which is used to generate a sine wave at the output. So, basically, it is of two types. First, first one is Wein Bridge oscillator and RC phase shift oscillators. These two are comes under RC oscillators, and it is meant for low frequency oscillation. First, we are discuss about the basic of oscillation, and in that one we are going to see about what is the criteria for the oscillation. So here I have given the figure which represent the canonical form of feedback system. Okay, so it consists of A and B, and you can see the V in and the output from the beta, that is VF, is subtracted, and it is you are getting the output at this point. Okay, so I can write A is nothing but V out by V in, and what is VF by V out? VF by V out is equal to beta. Okay, so here it employs a positive feedback. So first let us discuss about Wein Bridge oscillator in this video. So now what is an oscillator means? An oscillator is a circuit that produces a periodic electrical signals such as a sine wave or square wave. The application of the oscillator includes sine wave generators, local oscillators for synchronous receivers, etc. So it consists of an amplifier and a feedback network. So where an active device that is here an op-amp is used, and the passive component for feedback network, that is it is series, it is a combination of RC or LC. So to start the oscillation with constant amplitude, a positive feedback is not the only sufficient condition. Okay, it has to satisfy two conditions. One is the magnitude of A beta is equal to 1, that is called as loop gain. Okay, A beta is nothing but loop gain, and the phase shift around the loop must be 360 degree or 0 degree. Okay, so in addition to the LC oscillator, we have RC oscillators. So the two types are RC and Wein Bridge oscillators. So here let us discuss about Wein Bridge oscillators. So Wein Bridge oscillator is an audio frequency sine wave oscillators which is of high stability and simplicity. The feedback signal in the circuit is connected to the non-inverting input terminal, so that the op-amp is working as a non-inverting amplifier. So therefore, the feedback network need not provide any phase shift. So the circuit can be viewed as a Wein Bridge with a series combination of R1 and C1 in one arm and parallel combination of R2 and C2 in the adjacent arm. Resistor R3 and R4 are connected in the remaining two arms. The condition of the zero phase shift around the circuit is achieved by balancing the bridge. So now let us see about the circuit diagram of the Wein Bridge oscillator. Before that one, if you see, there is a series and parallel combination of RC network which will form a lead and lag oscillator. That is, at a high frequency, the reactance of the capacitor C1 and C2 approaches 0, which will causes C1 and C2 appear shorts. Here, the capacitor C2 shorts the resistor R2. Hence, the output voltage V0 will be 0 since the output is taken across R2 and C2 combination. So, at high frequency, the circuit acts as a lag circuits. So at low frequency, both the capacitors are open circuit because the capacitors offers high reactance. Again, the output voltage will be 0 because the input voltage is dropped across R1 and C1. Here, the circuit will act as a lead circuit. But at one particular frequency between the two extremes, the output voltage reaches to the maximum value. So at this frequency only, the resistance value becomes equal to capacitance reactance and gives the maximum output. Hence, this frequency is known as oscillating frequency. So now let us discuss about the Wein Bridge oscillator circuits. So here, if you see, it has a Wein Bridge network. You can see the V naught is connected to the one end and VF. Okay, the VF is taken at the another end. Okay, so you have a plus 2 and minus 12 volt as a supply voltage. Okay, so let me, so you can see R1 and C1 are connected in series and R2 and C2 are connected in parallel. So these two circuits will form a lead lag network. Okay, so from this I can write ZS is equal to R1 plus 1 divided by SC1 and ZP is equal to R1 in parallel R2, sorry, this is R2. Okay, R2 in parallel with 1 divided by SC2. Okay, so this is my circuit. Okay, if you see, um, so if I have given the, if this is my input, okay, and I can write so this R3 and R4 means you will get V naught by VA. What is V naught by VA? V naught by VA is equal to 1 plus R3 by R4. Okay, this is nothing but your A value. Okay, so here I can write A is equal to 1 plus R3 by R4. Okay, and what is beta? Beta is nothing but VF by V naught, right? So and we know that the loop gain is equal to magnitude of A beta is equal to 1. So what is beta? Beta is equal to VF by V naught. So and you can see this is my ZS and this is my ZP. Okay, so this is connected to V naught and here only you are getting VF. Okay, VF. So what is VF now? VF is equal to V naught into ZP divided by ZP plus ZS. So what is my beta? Beta is equal to ZP divided by ZP plus ZS. Okay. So what is ZP? ZP is equal to, I already told you, 1 by SC2 in parallel with Z2 and ZS is equal to Z1 in Z1, sorry, R2. R2 and this is R1 in series with C1. Okay, so if you substitute you will get, so if you substitute you will get R2 in parallel with SC2, right? So I can write R2 plus 1 divided by SC2 divided by R1 SC1 plus 1 divided by SC1 plus R2 by SC2 plus SC2 R2 plus 1 divided by SC2. So here R2 R1 is equal to R and C2 C1 is equal to C. So if you substitute, you will get beta is equal to R divided by SC by RSC plus 1 divided by SC. So this SC get cancelled out. Divide by CSR plus 1 divided by SC plus R divided by 1 plus RSC. So this I can write it as R divided by 1 plus RSC divided by 1 plus RSC square plus RSC divided by SC into 1 plus RSC. So these two get cancelled out. So this is my beta. Okay. So we know that A beta is equal to 1. So what is A? 1 plus R3 divided by R4 into beta. Beta is R divided by, if I maximize this equation, plus SC R the whole square plus RSC, that is equal to 1. So if you substitute SC, so R into SC, if you maximize this one, you will get these equations plus RC. Okay. So this, if I substitute S is equal to J omega. So if I substitute S is equal to J omega R3 by R4, J omega RC, if I bring this equation here, I will get 1 plus 3 J omega RC, because if I add this one, I will get 3 RC. So instead of S, I am substituting J omega. So omega square R square C square. So if I substitute J omega, I will get J square is equal to minus 1. So here, this is my one plus R3 divided by R4, that is equal to 1 minus omega square R square C square plus 3 J omega RC. So if you equate this imaginary term, okay, imaginary term to 0. So if I equate this imaginary term to 0, okay, I will get RC into 1 plus R3 divided by R4, that is equal to 3 omega RC. Okay, this omega RC get cancelled out. So you will get R3 by R4 is equal to 2. So R3 is equal to twice the R4. So my first condition. Next, from this equation, okay, substitute, make the real term is equal to 0. So you take the rest of the term. Okay, that is 1 minus omega square RC. So these are the term which is left out. R square C square. R square C square is equal to 0. So omega square R square C square is equal to 1. Omega is equal to 1 divided by RC. So what is my F? F is equal to 1 divided by 2 pi RC. So this is my frequency for the oscillation. So the advantage of Wein Bridge oscillator is it has very high stability and it has high gain due to two-stage amplifications, and we can change the frequency of oscillation easily by changing the RC networks. So the disadvantage of Wein Bridge oscillator is we can't generate a high frequency oscillation, and the practicality of the circuit which will causes frustration to the designers.